This is a Crouzet Valence TC125 lathe. It is really nice made and I enjoy working with it. I could not find many videos on the lathe on the internet, and most of the owners seem to be located in France. And the internet forums in which there are information are usually in French, which I do not speak. Mes amis français, je suis désolé, mais je ne parle pas français. When I read through the internet forums, it got clear to me that there is one weak spot of the machine. The gear driven by the lead screw. It is a replacement and alternative construction to a typical half nut and has advantages during normal work. But it takes all the load, no matter when turning the hand wheel of the y-axis or when cutting with mechanical feet. And here my exercise started. I decided to build an own gear to have a spare part, just in case of a failure in the future. Yes, and this is the result. But it was a long trip, and I want to show the details just in case you also need or want to do the same thing for your lathe. I never did gear cutting before, and the first part of the work was the planning and understanding of the different aspects of the task. There is plenty of information on the processing and the exact dimensions in the forum, and I decided to start with this information provided by the user JPC14 and especially Freddy007. These were really useful. Additionally, I watched some videos on the geometry of gears and also read different documents on the same topic to understand about gear modules, pitches and all the nice technical terms involved. I also tried to find a commercially available solution, but the worm gear in the Crouzet Valence is clearly a non-standard gear. Overall, I understood that for a smooth run of the gear, there are many things to obey, especially the information from the video channel Andy's Machines, which I will link in the video description, help to understand the differences of the different techniques. Basically, there are three different ways to cut gears. Straight cutting using a manual created cutter or a commercially available cutter, and the gear blank in that case is rotated by a rotary table or using an existing gear like in the method of JPC14 on the forum. Gear cutting using a hob. This can be done using a controlled turning motion of the cutter synchronized with the gear blank, like in the setup used in Andy's Machines, or in an uncontrolled manner where the cutter simply drives the blank by its own turning. And finally, gear shaping, which is a similar process to cutting keyways or internal slots. This is mostly to be applied for internal gears and in this way out of scope. From the theory, it gets clear that a gear cutting with a simple straight cutter having the complementary shape of the lead screw will lead to a non-usable gear. The result would be a rough feeling on the hand wheel, or turning will simply be impossible. The reason is that the gears will touch the lead screw when entering and exiting the same. You can see this in this picture, where the tip of the worm gear exceeds the limits of the lead screw. Hence, the tooth of the gear have to have not a simple regular, but a complex partly rounded shape. So I needed to decide on the technique to use. Building a gear hob seemed to be possible, since the Norton gearbox of the Crouzet Valence allows to cut a thread of 4 mm per revolution, exactly the same as the lead screw of the lathe. Building a straight cutter also seems to be no real issue. Cutting a gear from the gear hob requires to harden the hob, so I needed a technique to harden the steel of the hob. I have only a sloppy rotary table and I did not want to buy a proper dividing head. Also, I did not want to build an electronic drive for the same. Cutting the blank directly with the hob seemed to be a bad decision. The material of the gear is expensive and the hob needs to be in synchronized motion for an exact result. Hence I decided to go with a two-step processing. A straight cutter is used to cut the 40 grooves into the blank, leaving enough material to be removed by the hob. But the straight cutter gives a clear position for every tooth, respectively groove, of the gear, so that there is no problem with inexactness when the hob is used to form the exact form for the teeth. And since I do not trust my sloppy rotary table, I went with the technique of JPC14 to cut the grooves on the milling machine first. But before the start, the material needed to be ordered. For the gear I decided to go with bronze RG7 in 61mm. For the hob I went for silver steel type 1.2210 in 30mm diameter, which is of course the same as the diameter of the lead screw. I needed a big tooth gear with 40 teeth, and for the inside hole a 60mm reamer. Also I ordered a high-speed steel of 40mm square, with which I failed to do anything useful, and one of 3mm which I had laying around. And I needed some other material for holding the workpiece and some Loctite. Well, and then there was another side project, a hardening oven for the hob, which I always wanted to build, but this is a different topic and not part of this video. Also, it was a key point to be able to grind the cutter to exact shape, so the Tormek T4 whetstone grinder helped a lot to keep exact angles. After all this planning, the real work started with grinding the cutter at the Tormek. To do this, the lathe's lead screw needed to be measured to determine the angle and depth of the profile. Then the material of the cutter was cut to size, a 12mm hole was bored into it and it was glued to a rod. Then the hob could be cut. This was really hard. The cuts that could be taken were really shallow, and still I broke the cutter twice, which required regrinding. The overall procedure was taking a complete day, but I learned how to reposition the cutter to match to the existing groove and how to restart the process. I would recommend to get a higher and in that stronger cutter than the 3x6mm cutter blank that I used. It was too weak for the silver steel. I tried this procedure twice, once in mild steel, which could not be hardened, and the frustrating second time. Practicing the procedure on the mild steel helped a lot. And now let's have a look at what all went wrong, including the original cursing. And finally the depth of the cut was reached, the hub looked good and was the base for the further processing. All went well. The next step was then to cut grooves into the hub to have cutting edges for the final gear cutting. And then the hub was ready to be hardened. Then the blank was cut to dimension and brought to size. One issue with the blank is that the 100mm chuck I own can only hold the 43mm dimension in the inside jaws, and the outside jaws do not allow to access the part to be worked on when the blank is holding them. So there was no way than putting the blank on a 60mm rod with Loctite and working on this. And yes, I should have used a shorter one instead of the one which I later used in the milling machine. My original idea was to cut the rounding into the blank with a 40mm cutter in one pass. By this I would be able to grind the correct rounding to the cutter and transfer this to the blank. Well, this did not work as expected. So in the end I decided to use some cut modeling to determine some dimensions and cut some grooves to approximate the curve. That, together with some filing, was enough, since anyway the hob would do the rest in the end. Now it was time to build a straight cutter for the milling machine. There is not much special about this step, and it is described in many videos on the internet.
The only thing to obey is that the outer diameter of the cutter shall be 30 mm. Then a clamp for holding a rod with the gear blank on the one side and the 40-tooth gear on the other side was built from a piece of aluminum. This was cut to size, squared, and then a 20 mm hole was drilled in its middle. Finally, the square piece was cut into half at the middle of the 20 mm hole. By this, the rod can be clamped repeatedly in the exact same position in the vise. Then the angle for the straight cut was determined from the cut, and the head of the milling machine was set to 3.8 degrees. And finally, the mechanism to advance the gear blank by one tooth could be tried out, and the initial straight cuts could be made. Initially, the progress was somewhat slow, but after building some trust into the overall setup, the progress was okay, and the complete operation was finished in around 40 minutes. For the final gear hobbing, a small holder for the gear blank to be attached to the top slide of the lathe had to be built. The distance of the top slide to the center line of the lathe is 20 mm, and hence a base plate of 12 mm with a 60 mm rod was sufficient. Then the blank was mounted to the rod and secured by a screw.
Now all parts for the gear hobbing were available and the process was started. This went extremely well. It was absolutely simple and precise. The cuts that were taken were around 1/10 of a millimeter, and running the lathe for 3 rounds of the gear for depth of cut was sufficient. The size of the gear was repeatedly measured, and the procedure went on till the final dimension of the inner diameter was reached. When I came nearer to the final dimension of the gear, I also was confident enough to increase the speed of the lathe for the cut. The final result was really satisfying. The dimensions are matching the specification and the original gear. What was left to do was to bore the holes for the indexing pins and the screws. This time I decided to use a rotary table to hold the gear, and I needed to build a tool to find the center position, and a mandrel for the gear to hold the gear in the empty one center point of the rotary table. I will not go into the details of this, and looking back, I would have been better off if I would simply have calculated the positions and used the digital readout of the milling machine to bore the holes. But anyway, the result was good and the final assembly could be started. Turning the hand wheel was very satisfying since all the work paid out in the end, and even the initial try was a success. None of the expensive bronze was spoiled and some experiences were made, and the Crouzet Valence is ready to go for many years to come.